So really excited to be here. Thank you everybody for your introductions. It's really exciting to hear about what you do and the experience that you have. We are Santa Clara University, and our team, we call ourselves Bronco Solar just for fun. And we're really excited to show off what we have to show. So I hope it's obvious by now. Our district use case was the University of Central Florida. And I'm just going to run through our team. So first off is Karina, who couldn't be here today. She did the financial analysis and the financial modeling. She's a junior in electrical engineering. Trey, who is a first year graduate student in our power systems and sustainable energy program, who did the customer savings analysis and a lot of the battery design. Kashitij, who is a second year grad student with the power systems and sustainable energy program. Salvador, who is a junior electrical engineering major. Tim, Salvador did the ground mount system design. Tim is a first year graduate student for electrical engineering. I'm a senior electrical engineering major doing distribution with Tim. Carter is a first year graduate student in electrical engineering, and Mariela is a junior electrical engineering major who worked with Carter on the rooftop system design and who will be taking it from here.
Hi, everyone. Thank you, Danny, for the introductions. So today I will be presenting our conceptual system design. So after placing panels on all the UCF campus rooftops in our designated partition, as well as utilizing the top half of the ground mount area, our solar system totaled to 6.5 megawatt hours, which did not exceed our daytime minimum load. And of course, I want to touch upon some of the parameters we decided on implementing, which were mainly influenced by consulting a well-respected power industry professional and IEEE fellow, Leo Casey. For example, the types of panels our team decided on were the SPRE 20435 COM panels, which have a low degradation, a good power density, and a 25-year warranty, which means our system can last a very long time. Due to the fact that we opted out of placing trackers on our rooftop solar system, we did decide on having a 25-degree tilt south of the panel using a 18-inch row spacing in order to 1, maximize power generation, 2, reduce shading from other panels, and 3, to improve the ease of maintenance for the system. As for our AC to DC ratio for the system, this was set at 1.25, since a lot of our research pointed to the most economical and efficient ratio being between 1.2 and 1.3. And this happened to be the sweet spot for the cost of the system and the inverter and the amount of power that could be supplied. Of course, after implementing these parameters, our panels on our roofs had a solar access of at least 95%, and there was minimal to no shading on the panels. And as for our ground mount system, which is on the next slide, we utilized only the top half of the ground mount area in order to stay below the daytime minimum load. And as it happens, this worked perfectly because that way we would spend less on clearing the trees that were in the lower half. So a few assumptions that we made were that the Aurora software modeled the ideal weather conditions throughout the entire year, and that the cost of the system is tied to the financial summaries produced for a design. And we also assumed that the LiDAR and the irradiance applications on Aurora were accurately measured, and all the specs for our panels and our inverters were up to date. And so now I'll pass it off to Trey to talk about our storage system.
Thank you, Mariela. So yeah, as was mentioned before, we have 3 megawatt hours of battery storage. So part of the reason for this specific number was we knew we needed 3 hours worth to set off that extra load in order to avoid the high demand charges. So that was one thing, was to keep avoid any peak at any point. So using that battery storage to just offset that extra amount. And so for placement of these, we use them at the locations that you can see on the screen here. So one 1 megawatt hour is at the ground mount, and then the other units are each 500 kilowatt hour batteries. And those are there to prevent, we're having the over voltage problem on those transformers. And so that's the reason that we decided to split up the batteries and put them there, rather than have to, install an additional thing there, we may as well just put the batteries there and prevent that from happening. So if we go to the next slide, then we'll see just kind of a layout of roughly what's going to be happening, charging points, system, and then discharge. So one thing you may notice is that we have a simulated load. So the reason we did this was because our data that we had for load, a lot of it, like half of it, was during COVID. So we knew we couldn't trust that to be the actual accurate usage. So we took what we had for the first half of the year and then tried to, assume, okay, a little less is used in winter than summer. And it's not a perfect science for this. We did have to make some assumptions, but this is roughly what we figured was the best solution to it. And then so since there were no like specific limits on the battery stuff, we just did like a full charge, full drain to fully maximize out any of those possible peaks during the high demand times. And then if we go one more here, yeah. So, and then for the optimization, kind of like how we actually chose this stuff. Obviously, one of the big goals, minimize LCOE and LCOS costs. We knew we couldn't exceed the daytime minimum, which the 6.5 megawatts was what we considered safe, given that we, as said before, the data came from COVID. So we thought that was probably the safest number that we could choose confidently. And then lost it.
Sorry about that, Trey. I don't know what happened.
I'll keep going though. So there we go. Yeah, so then as we mentioned before, with those things, we knew certain places we chose the top half of the ground mount system and all those things, and just kind of all the ideal things that we could go with from that. And then on the next slide, here is our financial results. So I'll talk through this real quick because I didn't put all of the information. So estimated cost. So the system itself ends up costing around, we said 16 million, and that was including any of the, installation fees, every possible expense that could happen that even if it's not expected, if it was just a possibility, we put it kind of as the maximum amount. So with the assumption that probably at least I'd say half of that would be taken out on a payback, probably a 25-year typical 5% interest rate loan. But that number can be changed depending on how much is paid up front and all those type of factors. What we found is our minimum, absolute minimum savings, with the highest maintenance cost possible, like non-ideal weather and utility rates not increasing, like the bare minimum that you could save over the 25 years would be around 1.5 million. And then in a much more ideal situation, right, with rising utility rates, all the other factors, more predictable, better weather, everything like that, you can see upwards of like 10.5 million. If more of, and a lot of that also is if the less of the system is taken out on a loan, then obviously you get a better payback from it. And that's, yeah, as was said, that's kind of just the rough numbers though, because there's a lot of variables in that. And then next we'll just go on. Danny's going to cover the next part here for us.
Yeah. So for the distribution system impact analysis, it was interesting because as we'll see on the next slide, pretty much whatever we did with the PV systems and with the storage systems, I'm not sure if it's because the UCF grid is just very resilient, but we weren't getting a whole lot of over voltages. So that kind of eliminated one of the things we had to kind of compensate for with inverter controls. But then for overloads, this is something that really shifted a lot. So when we added all of our PV systems, it did create a huge increase in overloads for the system. And that was because at certain times of the day, the amount of power generated by the PV systems was higher than the transformer ratings of these individual buildings. And we figured it would be impractical to put a new transformer on each of these buildings. It was practical to do it for the ground mount, but for the buildings, we just put it directly onto the existing transformer, which led to some overloads. But once we added some of the battery storage systems, we were able to decrease those, because when the PV systems were overproducing and the load was too low, the batteries were able to kind of uptake that excess energy to prevent the transformer from being overloaded. So if we go to the next slide here, I just have two screenshots of the OpenDSS simulator. On the left, we see the heat map, and we see that, there aren't any areas in particular that look darker or thicker than any other. But more importantly, on the right, we see the voltage map, and at no point is it hitting the limits of 5%, 105% per unit, or 95% per unit. So one thing interesting about that was that I believe that these screenshots are for the last time step of the simulation. So it may have been more useful to look at how these plots change over all of the time steps. But when you look at the outputted CSV files, same result, some more overloads, but no overvoltages. In terms of innovation, we figured it's not typical to interconnect both the PV systems and the battery banks on the building transformers, rather than focusing on a dedicated location such as the ground mount first. We did create our ground mount, but we wanted to maximize the roof area, the usage of the roof area on the primary challenge area before moving on to the ground mount. We figured that this would help smooth out the grid impacts of adding these assets, rather than putting all of our power onto one transformer out in the ground mount, not really allowing power to be consumed locally by the buildings before being passed on through the distribution system. And also placing the batteries on the transformers, like I had mentioned, that are overloaded due to excess PV, allows us to keep the size of the PV systems high, even if the rated output of the PV systems exceeds the transformer ratings. Some things that we could have improved on were that, fully building out the ground mount area would have been a good idea, since this is a generally less expensive than most rooftop systems, due to costs that we didn't fully consider, like maintenance, permitting, fire safety, etc. And we had to add a transformer there anyways, which was expensive, but we were able to get a lot of power out of the ground mount without a whole lot of headaches. So that would have been something we could have taken more advantage of. And if we were to do that and really focus on the ground mount, that would have required more extensive siting and other development constraints on that area to really fully think about where can we place panels, where can't we, and in these areas that are kind of a gray area, what do we have to compensate for? And for rooftops, we should have used transformer ratings as an upper limit for the rooftop PV system size. Using batteries to kind of exceed that was a good idea, but if we could avoid that in the first place, that would have been something that would have been more resilient. And then finally, interfacing OpenDSS with either MATLAB or Python to get clear results and perform some iterative analysis for optimization. That would have been great. Definitely something that is technically difficult, but it would have been really satisfying to see the results of that. And that's it.